Today, we all have gathered here to celebrate International Year of Quantum Sciences and Technology 2025. 2025 marks a turning point in science and innovation as we celebrate the International Year of Quantum Science and Technology. We recognize the power of invisible forces shaping our future. I remember the great Maratha warrior Chhatrapati Shivaji Maharaj and pay my tributes to Dr. D.P. Khandelwal sir, who initiated Indian Association of Physics Teachers. Respected Professor Ahluwalia, Professor O.P. Chimankar sir, our fellow friends from Shivaji Science College, Nagpur, Shivaji Science College, Amravati, and I guess many more connections throughout the Vidarbha. Today, I'm at postgraduate teaching department of physics at RTM Nagpur University. Rashtrasant Tukdoji Maharaj Nagpur University, formerly known as Nagpur University, is one of the oldest and most prestigious universities in central India, established in 1923. With the legacy of academic excellence spanning over a century, it has nurtured generations of scholars, scientists, and leaders. The university is known for its strong emphasis on research, innovation, and inclusive education across diverse disciplines. Its commitment to quality education continues to inspire institutions and students across the nation. Rashtrasant Tukdoji Maharaj Nagpur University has produced numerous distinguished alumni who significantly contributed to various fields. I want to list a few of them. Professor P.V. Narasimha Rao served as 9th Prime Minister of India. Justice Muhammad Hidayatullah held the esteemed position of Chief Justice of India and later served as Vice President of India. Nitinji Gadkari is known to all of us, who is Minister of Road Transport and Highways. Harishankar Parsai is a renowned Hindi writer and sitarist. Sonu Sood, an acclaimed actor in Indian film industry. These individuals exemplify the diverse talent nurtured by RTM Nagpur University, making significant impacts in their respective domains. To cite one example of physics department, one of the alumni of this department, Professor Arun Nigvekar, was chairman of UGC who was mentored by a legendary teacher here, Professor C.M. Mande. I would like to say a few words about the Sub-Regional Council for Vidarbha. Being president of SRC for Vidarbha, I would like to mention that our team has started working since January 2024, and these are our baby steps through which we are reaching to teachers and students of Vidarbha. It is my duty to introduce today's speaker, Professor P.K. Ahluwalia, sir. Professor P.K. Ahluwalia is a distinguished physicist and academician whose contributions have left a lasting impact on science and education. A former faculty member at Himachal Pradesh University, Shimla, Professor Ahluwalia held several key positions, including Dean of Physical Sciences and Dean of Planning and Teachers Affairs. He played a pivotal role in academic governance, including services on Himachal Pradesh State Higher Education Council and various regulatory advisory bodies. With deep interest in condensed matter physics, his research spans magnetic alloys, quantum dots, low-dimensional systems, resulting in over 120 publications and 3 authored books. He also mentored numerous postgraduate students and has authored and has been an adjunct faculty member at the institutes such as IIIT Vadodara, and UGC Inter-University Acceleration Center. Professor Ahluwalia is a recipient of Commonwealth Academic Fellowship, through which he worked at University of Edinburgh and has been recognized with a Best Teacher and Academic Administrator Award, among others. Beyond academia, he is passionate about science communication, travel, and public engagements. Currently, he serves as president of IAPT and is actively involved in scientific societies like Indian Association of Physics Teachers and Vigyan Bharati. Professor Ahluwalia truly embodies the spirit of scholar, educator, and a visionary leader. So I wish the audience to give a applause. Now I am going to hand over to Professor Ahluwalia sir for next proceedings.
Thank you. I hope I am audible to the audience in the hall. Am I audible?
Yes, sir.
Okay, fine. Wonderful. So, dear students, esteemed faculty members at the Physics Department, University of Nagpur, and the students who have joined from other very prestigious colleges of Vidarbha region, their teachers, head of the Physics Department, Nagpur University, President, Sub-Regional Council, Vidarbha of Indian Association of Physics Teachers, Professor Anwane, Vice President, Sub-Regional Council, Vidarbha, Professor Gobinda Lakhotia, and all the participating colleges. At the outset, I must thank each one of you for participating in this particular program, which is part of the celebrations of International Year of Quantum Science and Technology. Dear students, I think we cannot imagine today the way we live without what quantum mechanics has done in the last maybe 125 years. Though the word quantum mechanics was coined 100 years back in 1925, ever since we have found that quantum mechanics has changed the worldview not only of physics, but of almost all the things which are there around us in this world and in this universe. So there is nothing which has been left untouched by quantum mechanics. Let me tell you the genesis of this program itself so that we may appreciate what we are going to do next and see that how we are going to do this. IAPT, which is a 40 plus years old organization of teachers and students, is very much interested in bringing awareness about the importance of the impact of quantum mechanics in the last 100 years. And in fact, we feel this as our bounden duty to do whatever we can possibly do to meet the objectives of International Year of Quantum Science and Technology. So this is one part of why we are meeting here today. There is another thing which is there, which is very much at the top of my mind, and that is that the students who are participating in this particular program, they belong to undergraduate departments of the physics, and they also belong to the postgraduate departments of the universities and colleges. Now, I think it is your duty also that whenever you get any opportunity to tell people that why we are celebrating International Year of Quantum Mechanics, you should be in a position to tell them that this is the importance of this particular celebration, which is going to continue for whole of the year. So this was one uh, other point which we had in mind, so that students may become part of this awareness program throughout the country. You should be in a position to visit schools. You may be in a position to visit other colleges where you are. Same is the case with the faculty members also who are around in this particular program. I am really grateful that Sub-Regional Council Vidarbha of the IAPT took this initiative to bring together a large number of students and teachers for this particular program. If you ask me, what am I going to talk to you? Maybe you have an inkling of the topic which I am going to share with you. You will notice that there are two things which I have in mind while making this connection with you. One is this, that I should really try to bring to you the history of the development of the quantum mechanics itself. And one person who was at the bridge where old quantum theory and new quantum theory was actually meeting was de Broglie. Normally in India we call him as de Broglie, but in French his name is pronounced as de Bro. So de Bro is a very interesting character in the development of the quantum mechanics itself. And whenever anybody asks us, do you know the de Bro's formula? Everybody is able to tell us, yes, lambda is equal to h upon p is a well-known formula. But this formula actually changed the people from Bohr's world of quantum mechanics to the modern quantum mechanics, if you allow me to call it like that. There is another thing which we are actually experimenting in this particular program, dear students. I would like to draw your particular attention. I hope you have mobiles with you. And these mobiles we are going to use in today's program as what you call clickers, in the sense that within few minutes, we will be flashing a QR code on the screen for you to take a picture and reach a Google form and attempt the questions given in that Google form around de Bro's hypothesis itself. And let's see how many of you are able to do it. It is like a pre-test program for you. So please get ready and hold your mobiles in your hand. Professor Govinda Lakhotia is going to share with you on the screen that QR code. It is a kind of a pre-test. At the end, we will have a post-test also. So I hope you are able to see the QR code. Just take a shot of it and see that you are able to reach the Google form. We will give you 10 minutes to attempt these questions. After that, I will begin my lecture further. So I am now keeping quiet. I'll give you time to attempt the question itself. It is 12:45. I'll come back to you at 12:55. 5 minutes more.
Sir, we cannot see your screen.
Okay, I am sharing right now.
Your WhatsApp screen is now on the screen.
Okay, I'll come back and
And everyone,
is it visible now?
not yet.
Is it?
Yes, sir. Yes, sir. It's visible now.
So I think time is up,
Yes.
and maybe I can begin.
Yes, sir.
So may I start?
Yes, sir.
Okay, all right. So I hope you are able to see on the screen the title of today's lecture, From Hypothesis to Technology, Louis D. Bro, the Legacy. Dear student, there is another element which you will see as I will proceed with the lecture. You know, when in IAPT we thought that we should bring awareness program for quantum mechanics, I thought that can we really engage with students in some different way? And I'll show you in the end that what was the different way. I thought of creating doodles. Doodles are nothing but, line sketches through which you try to convey some kind of a story. And the doodles which I will share with you later is the story of this de Broglie's hypothesis and how it led to the emergence of a technology. Dear students, let me tell you that that was one of the first quantum technologies which were brought in the market and was sold worldwide. Very few people actually know about it. My outline of the talk is as follows. I have already talked about the motivation of this particular lecture. I will talk about how this quantum era begins and how Bohr's quanta tremors actually start happening. Einstein started thinking about it and was not very happy with the way it was developing. And it was at this point that de Broglie entered the scene and brought a new thing on the table. It was a sheer, what you call, a play of intuition when he brought this idea before people as a graduate student. At that time, he was actually pursuing his doctoral degree at Sorbonne University, Paris. And that is where he actually talked about a unifying principle of the nature and brought the idea of a wave packet, phase velocity, and group velocity. And he also tried to explain that how this wave packet builds up, made use of what you call as a Fourier analysis. And then we saw that a new idea emerged, which we call as the wave-particle duality. And as a result of this, he really tried to look at Bohr's atom in a very, very different fashion. And that was that can we really treat an electron going in an orbit in the Bohr's planetary model as not just a particle, but as a wave which is spread over that path which we have been trying to describe as the path over which the electron is moving. And then we will come to the doodles, where I will try to talk about how technology actually emerged. So I hope you know that in the year 1900, when people were feeling that maybe whatever we wish to know about physics is already known to us, it's a matter of solving equations. And if we have, say, good computers on which we can put these equations, we can solve almost all the problems which are there to be looked at from physics eyes. But there was one problem which was always disturbing people. And that problem was actually a result of the study of spectrum of atoms. It was not just a new study. People have been knowing a lot of results as far as the spectrum of atoms and molecules was concerned. But there was one very interesting experiment which was motivated by Kirchhoff, where he created a very interesting concept of a black body, which was actually kept at a certain temperature. And then they tried to look at the infraradiation spectrum of that black body itself. Now, you must be seeing on this screen on the right-hand side that famous graph which people were getting as a spectrum of the black body radiation. Very small part of that was actually lying within the visible range also. And you can see some characteristic features of this particular curve. That part of it was before the violet part of the visible range called violet, ultraviolet region. And part of it was in the infrared region, and part was in the visible region. Now, to explain this, which was becoming a kind of a riddle, Max Planck, who was very much trained in thermodynamics, tried to think about a strategy and tried that, let me try to explain it. And during his calculations, where he was using a very interesting model to describe the black body, and that was that black body's walls are composed of nothing but a collection of harmonic oscillators, he arrived at a formula. But one thing which was missing in that was that he needed a kind of a constant to match his theoretical results with the experiment results. And after a lot of deliberations in his mind and calculations, he came across this constant, which we today call as the Planck's constant. And he said that the energy which is there of these harmonic oscillators is actually quantized, and it depends upon its frequency at any given time. And he introduced the idea of quantization of energy. And he wrote a paper which was titled On the Theory of Law of Energy Distribution in the Normal Spectrum. And it is here that he used the word quantum, which actually means how much. Today, when we try to describe quantum, we actually mean a packet of energy which is emitted or absorbed by the atoms. Now, in next 5 years, there was another fellow who was very young. He came on the scene and he was fascinated with this idea of the packet of energy. And he made a very, very bold step forward. And he saw that if he has to explain another very interesting physical phenomena called photoelectric effect, he has to take a big leap. And he brought in the idea of something which was not very much anticipated at that point of time, back on the table, which was at one point of time even floated by Newton. Newton had tried to describe light as nothing but corpuscles, that is particles. Albert Einstein was also talking the same thing. And he wrote this one-line formula and tried to explain with it all the laws or the observations related with the photoelectric effect. Formula is very simple. It says that if we let a light which is having a packet of energy h nu, where nu is the frequency of the light, it gets used up in two ways. Part of it is taken up to bring an electron on the surface of the metal. The metal was the one which was being exposed to that kind of light. And rest of the energy actually goes into the electron to give it the kinetic energy. And I think it was a success story beyond doubt. Now, in 1913, Niels Bohr picked up this idea of Planck's constant. And if you, dear students, look at this Planck's constant, you will find it has got the dimensions of angular momentum. And he brought a new model of atom, which was very different from the earlier models of atom given by J.J. Thomson and modified by Rutherford, where Rutherford had said that atom has got a very small area in which most of the mass of the atom resides, called nucleus, and the electrons are spread around it in the form of a jelly. What Bohr did was, he said, the electrons are not in the form of the jelly, but they are actually moving in definite stationary orbits. And he even gave a formula that how these electrons get distributed. And that formula is very well known to us. That is known as the Bohr-Bury scheme, by which you can definitely calculate that in first orbit there can be 2 electrons, in the second orbit there can be by that formula, if you calculate 2n square, the number of electrons actually keep on going as you go to the new and new orbits. And this model of atom actually was based on the fact that there is a force which is actually keeping this electron going around the nucleus, and the origin of that is electrostatic force. And he, in his postulates, brought in two things. One was that these orbits, which he tried to describe as stationary orbits, are the ones in which the electron normally resides is decided by the fact that the angular momentum is quantized for each of these orbits. And that is why this formula mvr is equal to nh bar actually emerges. Using this, he calculated the energy of an electron in a given orbit. And he found that this is equal to minus 13.6 electron volts divided by n square, where n is the principal quantum number. And from here, he found that he can also describe how the light is emitted or absorbed by an atom, and gave back us nothing but Rydberg's formula. Now, the moment this came on the scene, you know what happened. We found that the energy distribution in the atom was having discrete nature, starting from ground state. This 1 upon n square makes sure that these energy states are not equidistant for each other, but they are, as we go above, they become narrower and narrower. And once this came on the scene, people came forward to test his hypothesis. And what was found was this, that Frank and Hertz in 1914, immediately after the enunciation of Bohr's model, demonstrated this quantization of energy, in which they were able to show that energy can be absorbed in specific amounts and also given out in specific amounts. Now, this was a great, great success story. Everybody was happy that at least hydrogen spectrum has been completely explained. But this story could not go beyond hydrogen. When it came to multi-electron systems, the Bohr's model actually did miserably. And at one point of time, Niels Bohr made a statement where he said, anyone who is not shocked by quantum theory has not understood it. So this was a kind of a shock which was generated by the Bohr's model. There were other people also who actually later for 6-7 years kept on working on this model. And one of the very prominent persons was another German physicist, Arnold Sommerfeld, who actually said, why have circular orbits as Bohr is saying? We should have actually elliptical orbits. And maybe that is going to give us more accurate description of atomic spectra. You know, it was like looking at how finely we can actually calculate the value of the energy levels of different orbits. And he introduced a concept called the quantization of azimuthal quantum number L, which described the shapes of these orbits on which electrons were actually moving. He was also able to bring in the special theory of relativity in his calculation, and was able to explain the fine structure also of the hydrogen atom. He also tried to go beyond hydrogen, tried to look at multi-electron atoms, but not much success was there. Let me tell you how people were feeling at that point of time regarding these developments. Try to see what Albert Einstein said in 1913. He said, if it is correct, that means if the Bohr's model is correct, it signifies the end of physics. Heisenberg said, perhaps this is madness, but it has method. Pauli said, physics is a blind alley again. In any case, it has become too difficult for me, and I would prefer to be a comedian in a cinema or something like that, and hear me know more about physics. Max Laue and Otto Stern. I hope you have heard about Laue patron, and you must have heard about Otto Stern also, Stern-Garlick experiment. They said we would give up physics if in that nonsense of Bohr there is at least something. So what were the Einstein's contemplations? Let's once again go back to that. He said, and he made a very, very big leap, that light has a particle nature. And when he presented his paper of 1905, actually he used a very interesting word, heuristic viewpoint. Heuristic is a term which normally people use when they want to put forward an idea, but they are not very sure that how this will be taken by people. In 1909, he once again visited that idea, and he stated in one of his papers, "It is my opinion that the next phase in the development of theoretical physics will bring us a theory of light that can be interpreted as a kind of fusion of the wave and particle theory." Now, I hope you can see that already this is a kind of a premonition which is coming through the words of Albert Einstein, where he was seeing both particle nature and wave nature coexisting. And it is here that Louis de Broglie enters the scene. He was basically a prince, and he had his early life and education in Paris. He was born in 1892. His family was a rich, noble French family. He was initially inclined towards history and politics. Look at the twist of the things. He later pursued theoretical physics under the influence of his brother. His brother was actually a physicist. And his brother used to go to the conferences. And one of the conferences which his brother had already attended was the Solvay conference, the first Solvay conference, which is a very historical landmark in the history of the development of quantum mechanics itself. He also studied from a very famous theoretical physicist in France, Poincare, and he attended Poincare's lectures on these two subjects, electrodynamics and thermodynamics, also classical mechanics. Now, as it happened, because his brother had attended first Solvay conference, he could put his hands on a report of that with his brother. And by chance, he read through it. And that is what brought him into a kind of a inquisitiveness regarding quantum theory. So he got interested in quantum theory as a result of that. There is one thing which we should really not forget, that life has got its own turns and twists. When he was actually studying and he was free, he was working with his brother, World War I actually happened. During this World War I, he, because of his training by his brother, whose picture you can see on the screen, Maurice de Broglie, served at the radio telegraphy station at the foot of the Eiffel Tower. And he was responsible for maintaining the equipment used for sending wireless transmissions. His training under his brother served him well during this period. Now, after the war, you know what Louis started doing? He collaborated with Maurice on experiments related to X-rays and the photoelectric effect, which led to the publication of his first papers on the underlying quantum theory. So now you can see how the development of the understanding of photoelectric effect by Einstein was influencing the physicists at that point of time itself. Now, I would like to come to a very interesting thing, that how our intuition starts working. In fact, it has been there for quite some time in physics. There are certain ideas which come out of intuition only. And one example which I want to give you is about how Faraday actually discovered the phenomena of electromagnetic induction. And it was after 10 years of the experiment which Ørsted did, and which is very well known to any physics student. Ørsted had done one experiment in which he had shown that if we take a current carrying conductor and if we let that conductor pass through a cardboard piece, and if we hold that cardboard piece with iron filings on top of it, and if we tap the cardboard, these iron filings actually start forming concentric circles around the hole through which that current carrying conductor is passing. So the basic idea was this, that a current carrying conductor has got a magnetic field around that. Faraday actually asked an opposite question, and that was, if there is a magnetic field, and if we place a current carrying conductor in a conductor in that, not current carrying, can we really see a current being generated in that? And he designed a very simple experiment. Any high school student can do that. He took a copper wire made a coil out of it, placed a magnet inside it, attached the two ends of the copper coil with the galvanometer, and he was waiting for the electrons, which were not at that point of time known, waiting for the current to flow in it. It was very interesting. Nothing was happening. Out of frustration, he picked up the magnet out of the coil and threw it back in it. And lo and behold, what was happening? He saw that the galvanometer's needle showed a deflection. When he took it out, again it showed a deflection, but now this time deflection was in opposite direction. This was a eureka moment for Faraday. This is precisely what started happening in the mind of de Broglie. In 1923, he wrote in a very interesting fashion that he was having long reflection in solitude and he was meditating. And he said, I had suddenly had the idea that the discovery made by Einstein in 1905 should be generalized by extending it to all material particles and notably to electrons. And he further said, even a simple water wave is granular at the atomic level. So he was actually trying to imagine in his mind that a water wave is also made up of atoms, and a wave is associated with these particles, which we call as atoms. So he reasoned, since it is composed of the coordinated motion of a horde of water molecules, all particles and all waves are in fact a mix of both. Because their wavelengths were so small, such matter waves would not affect the macro world or what we call classical world. Their effects would only appear at the atomic scale. Now, this slide which you are watching is a very interesting slide where you can see how the mind of de Broglie was working. The way Oersted was an inspiration for Faraday, Einstein turned out to be an inspiration of de Broglie. And then he focused on this problem for his doctoral thesis. And in 1924, which was much before Heisenberg, Schrödinger, and Dirac came on the scene, to build the quantum mechanics proper, or matrix mechanics or wave mechanics, he wrote, it would seem that the basic idea of the quantum theory is the impossibility of imagining an isolated quantity of energy without associating it with a certain frequency. However, it is difficult to understand precisely the physical sense of the frequency in the Einstein equation. But he further said, it apparently describes a certain internal cyclic process. Now, these words are full of philosophy, in fact. He was not deriving anything. He was just contemplating on an idea. And in his thesis, therefore, he enunciated a great unifying principle of all of physics. And this is where, for the first time, in a doctoral thesis, somebody started talking about wave-particle duality. And he wrote, I am convinced that the wave-particle duality discovered by Einstein in his theory of light quanta is absolutely general and extends to all of the physical world. And it seems certain to me, therefore, that the propagation of a wave is associated with the motion of particles of any sort. And he hyphened that with photon, electron, proton, or any other. I think this is a great quote from his thesis itself. And in his thesis, he tried to attach waves with the particles. And he called these as associated waves. And to these waves, de Broglie assigned a frequency that accompanied the particle through space and time, which were like pilot waves, which guide particle in its motion. So try to imagine as if somebody is carrying in a wave packet. Imagine that wave packet in the form of a car in which electron has been put. You are not able to see the electron, but you imagine that whole of the car is moving around and giving you a feeling of motion. And then he asked himself this question, can these pilot waves be measured? And de Broglie said, yes, these can be measured. And he enunciated three things in it. One is phase velocity, speed at which individual wave crest moves, group velocity, which is speed of the reinforcement regions formed when many waves are superimposed, and this is nothing but the speed of the wave packet. Dear students, it is here that for the first time, we once again try to see the principle of superposition coming into play. And then he further mentioned that velocity of particle reinforcement region displays all the mechanical properties. For example, energy, momentum. So he was able to give an analogy. Pulse that is produced by superposition of many waves of different frequencies. This is where actually he applied the Fourier analysis. We all know that Fourier analysis is at the heart of understanding superposition of waves. You know that in your function generator in the lab, when you try to create a special waveform, that is nothing but the result of superposition of very many waves. Now, this was his method. He said, assign an electron a couple of waves with different wavelengths. The wave making up the electron is then obtained by adding all these partial waves with different wavelengths. It emerges that the uncertainty in momentum, that is in speed, simply implies that we have to superimpose within a wavelength range, and the result is a wave packet. If we add waves with a certain wavelength band the correct way, a localized wave packet results. This implies that the individual waves, which might be widely extended, cancel each other except in a small region. This small wave packet corresponds to nothing but a particle. The extent of the wave packet then gives us probability of finding a particle when some measurement is performed of its position. Now, see, these are very interesting things which you are actually hearing. It was here he was talking about what will happen when we are going to measure something in quantum mechanics. Measurement is something which we take with a lot of caution in quantum mechanics. You know Heisenberg's uncertainty principle. It says that the two canonical variables of position and momenta associated with a particle are such that if you try to find very precisely the position of the particle, you will lose the information about the momentum. And if you try to measure momentum precisely, you will lose information about the position itself. And now you can imagine, how small wave packet can be made. Small wave packet actually means less position uncertainty, but large momentum uncertainty. Medium wave packet means medium uncertainty in position, medium uncertainty in momentum. Large wave packet meant large uncertainty in position and small uncertainty in momentum itself. I think you are getting a recapitulation of the idea of Heisenberg's principle. Heisenberg is not yet on the scene, but in the seeds of the thoughts which were given by de Broglie, all these ideas were already in place. And then he did a small calculation, and from there he arrived at this formula which we call as de Broglie's formula. De Broglie's formula which relates wavelength of a wave with its momentum. And here these two are inversely related. The wavelength of light is decreased, the momentum of the photon is increased. In fact, this is true for all particles, he proclaimed. Actually, his thesis advisor was Paul Langevin. Those students who have studied magnetism at the undergraduate level or at the PG level, they must have heard about the name of Langevin. He was a person who did a lot of work in magnetism. When this thesis went on his table, he was completely baffled, confused rather. And Albert Einstein was one of the, thesis evaluators. But he sent an advance copy to Albert Einstein to have his opinion. And Einstein told him, as I mentioned earlier, in 1909, he had made a statement of wave-particle duality. He gave his nod. It's a wonderful thesis. Go ahead. he also communicated this to Lorentz. I hope you know the name of Lorentz also, Lorentz transformations fame, saying, I believe de Broglie's hypothesis is the first feeble ray of light on this worst of our physics enigmas. PhD committee recorded later, de Broglie has lifted the great while. Actually, that means that parda ut gaya hai and declared him pass. Now, in physics, we don't believe when somebody comes and says that, look, this is something which will happen. Why Einstein got a Nobel Prize in physics on photoelectric effect? Because it was already experimentally there. He gave a wonderful theory to explain all the things associated with the photoelectric effect. But in the case of de Broglie's hypothesis, it was yet to be tested experimentally. So people started asking this question that let us design an experiment and see whether we can confirm what de Broglie is saying. And there were two people who actually came forward. One was Davison and Germer and team. Another was G.P. Thomson. By the way, G.P. Thomson was son of J.J. Thomson. What Davison and Germer did was they did a scattering experiment. Whereas what G.P. Thomson did was he did a diffraction experiment of transmission. And actually this transmission he did on a thin foil of a metal which was made up of tiny crystallites. So it was a polycrystalline material. And as a result of that, we were able to see these rings appearing as a diffraction pattern. Whereas Davison and Germer actually took a nickel crystal, and this nickel crystal they were able to use because before them, Lave has already given them an idea that crystals are nothing but stacked planes of atoms. And the distance between them is just right for doing any diffraction experiment. So they actually tried to do this scattering experiment. And once again, they confirmed that yes, it is experimentally possible. Now try to see what de Broglie had done to the Bohr's model. He said, I am not going to treat now electron as a particle going around in the orbit. He said, I will associate a stationary wave with it. So in the picture on the right, you can see that there are stationary waves. You can see their crests and troughs, but it is a stationary wave. It is not a progressive wave. And it is just there on that circumference of the orbit itself. And he also said that for n is equal to 1, there is one wave. For n is equal to 2, there are two waves. For n is equal to 3, there are three waves. And the formula actually, which he wrote, he said that the wavelength lambda 1 must be associated with the circumference 2 pi r1. Twice the lambda 2 must be associated with 2 pi r2. Thrice the lambda 3 must be associated with 2 pi r3. So how he could see from here that with each circumference, a particular wavelength or a particular frequency was associated. And that meant a particular energy was associated. It's a very simple formula. You take this 2 pi r is equal to n lambda, go back to Bohr's postulate on angular momentum quantization. Lo and behold, you will find that formula of the de Broglie will emerge. Now, the beauty of this idea and its confirmation actually gave Schrödinger something to look at, and he picked up the threads further. Mind it, de Broglie wrote his thesis in 1924. De Broglie comes on this, Schrödinger comes on the scene in 1926, and he posed a very simple question. He said, when already we are saying that there are matter waves, can I develop a wave equation for matter waves the way we have, the wave equations for various phenomena in physics, like for example, wave equation for an electromagnetic wave. And this is how the wave mechanics and the wave equation were born. Just within 2 years, there was a new thing which was put on the table. And from here, I come to the idea of the doodles, which I have been talking right in the very beginning. So when I started thinking about it, that to bring an awareness of these programs among students, what I should do. So I thought, let me really create some doodles. Now, these doodles you will find are very, very simple things. They are basically sketches only. And if you start watching it from the top, you will find that I have drawn de Broglie. Matter wave hypothesis is gave. His life journey's time interval is given. And I am explaining that he was the one who said, give me the momentum of a particle, I will give you the wavelength. And then series of minds come together to test the hypothesis. They were actually talking with each other and they are saying, to believe, we must test what de Broglie is saying on the holy grail of science, that is experiment. And on the other hand, G.P. Thomson, who was son of J.J. Thomson, the discoverer of electron, he said, if electrons are waves, they should diffract. If it happens, it will also give us a proof of Schrödinger and Dirac's wave theories. You know, it is happening in 1927. Already in 1925, Heisenberg had given his matrix mechanics. Schrödinger had already published a paper and had made known the wave equation, which we call as Schrödinger's wave equation, to the people. Dirac actually took a step further and brought in that wave equation the idea of relativity. And he was able to, tell us a consequence of the, a particle called positron, which is nothing but an antiparticle of the electron itself. So this is how we actually move further in this particular idea. Now, saying this, that we want to design an experiment is not that simple. So who were the people who were involved in, designing these things, these kinds of experiments? And who were the people who actually helped them? Now, one person who was there who helped in creating a source of electrons was J.A. Fleming. He actually is the man who did a lot of work in the development of the vacuum tubes also. And he actually converted this formula of de Broglie, in which you can see in this formula, he is talking about the accelerating potential of the electron, mass of the electron and the charge of the electron. They are constants. Planck's also is visible in it in the form of Planck's constant. And he found that this wavelength is tunable. That was a wonderful thing. That means if you have a stream of particles, if you can accelerate them, their wavelength also changes. So by fixing the accelerating voltage, you could choose what kind of waves you are going to get corresponding to the electrons. So he is saying change accelerating voltage to change wavelength of the electron wave. He remained in his life journey from 1849 to 1945. So there is another very interesting, there is a small emoji who is saying, oh, so electron waves are tunable. You can have electron waves of desired wavelength. But to do this experiment, there was another thing which was there, which was happening. And that was because of Max Lowe. He actually revealed the crystal periodicity through his X-ray diffraction experiments. He proclaimed that atoms in crystals form space lattices. And this small, doodle is showing how these lattices are sitting on one on top of the other with a lattice spacing of d, which is of the order of angstroms, which is typically of the order of the wavelength corresponding to an electron. So what he was precisely saying was this: crystal planes have between them tightly spaced openings ready to act as a diffraction grating. And mind it, it was Max Lowe who actually gave birth to the solid state physics experimentally, and it was in 1912. Another emoji is coming, who is actually looking at a quote of Davison and Germer. if electrons are waves, crystal should be the best choice as gratings. Now, Davison did their experiment, Davison and Germer, G.P. Thompson, and here in this doodle you can see a comparison. Both did their experiment in 1927. They got a Nobel Prize on that in 1937, 10 years after that. Davison and Germer did an experiment in which electron beam was scattered, whereas G.P. Thompson did an experiment in which electron beam was being transmitted. Davison and Germer also saw a diffraction pattern through the detector on a nickel crystal, and G.P. Thompson saw diffraction rings, as I explained you before. The result of Davison and Germer was given in the form of these peaks, which showed the variation of intensity, showing that kind of a diffraction where you see high intensity and low intensity regions. Whereas in the case of G.P. Thompson, he used a gold foil target, which was nothing but microcrystals in the foil, which were leading to this ring pattern. Why these rings? Because we were seeing simultaneously many micro crystals arranged randomly causing diffraction. The Davison and Germer experiment happened in AT&T Bell Labs, whereas G.P. Thompson did this experiment in the University of Aberdeen, Scotland. And then you can see Emoji once again sitting here and telling you, Louis de Broglie's hypothesis stands verified. You can trust electrons behave like waves. And there is a small remark below, so do neutrons, beam of helium atoms. Now, I'm coming to the technology part of this lecture itself. The moment people started saying that electrons are waves, which are being stated here, hurrah for the electron waves. We are ready for electron optics and emergence of a new technology and a new device. So this happened when this idea came in the hands of two engineers. One was a teacher and other was a student. And they are the two teacher and student team who brought electron optics on the scene by inventing what we call as the magnetic electron lens. The name of the teacher was Max Knoll. He actually lived from 1897 to 1969. And his student was Ernest Ruska, who actually lived from 1906 to 1988. And you know, the fundamental thing which resulted as a result of that, which we see in televisions and CRTs, today we are seeing different kind of television screen. Earlier we used to have a cathode ray tube in our home, on the screen of which picture used to be painted by the electrons. So they were knowing that if we think of a wave, the resolution of the optics as a result of that is inversely proportional to the wavelength. Smaller the wavelength, higher is the resolution. So that meant that electrons can be used for seeing highly resolved images of anything which we see under the electron waves. Resolution actually means, which is also written as a small note on the side, minimum distance between 2 points that can be distinguished as separate. So one very fundamental idea which is there is that wavelength of the electron wave is very, very much less than the wavelength corresponding to the visible light. So now the question was, can electron moves be used to achieve better resolution than optical waves in a microscope? And already, you know, these kinds of things were there. They made use of this Abbe's diffraction formula, which says yes, and a quantum technology is born named transmission electron microscope in 1931. They, you know, immediately talked about this machine with what you know as a big German company, Siemens. They were the ones who first of all converted their prototype electron microscope into a microscope for the market itself. And there were many people who were ready to buy it, particularly biologists, botanists, geologists, they came forward to buy it. Now, just for your comparison, the resolution limit of these optical microscopes is what? From 200 to 300 nanometer for visible light. Whereas in an electron microscope, you can go from 0.1 to 1 nanometer, limited by wavelength of the electron wave. But mind it, electron wave is tunable. Its wavelength can be tuned. So this is in just 3 doodles, you can see that you can explain whole of the what you call de Broglie's hypothesis and its implication and how it resulted. By the way, let me also tell you that de Broglie had a wonderful relationship with India. He was the first person to win Kalinga Award. I don't know how many of you know this. Kalinga Award actually is a UNESCO Kalinga Prize for the popularization of science and is an international distinction that recognizes outstanding contributions made by individuals in communicating science to society and promoting the popularization of science. Established in 1951, this award is UNESCO's oldest prize, created following a donation by Mr. Bijoyanand Patnaik. I hope you have heard about Biju Patnaik, father of Naveen Patnaik, he was. And he was the one who actually made this contribution to give this prize. And he was the president of a Kalinga Foundation Trust. And Kalinga is a landmark in the history of our country, connected with Ashoka, where he actually fought a war and then got completely dejected, and he just uh, went away from the wars itself. This prize is given annually to individuals who have had a distinguished career as writers, editors, lecturers, or film producers, and have championed communicating and popularizing science, research, and technology among the public. De Broglie got this prize in 1952, almost after 25 years of his discovery of the hypothesis. So I'm at the end of my lecture, dear students. These are some of the references which I have used for creating this. The doodles I actually sketched myself, and I was really very happy when I saw how we can convey a very simple concept to the lay people, maybe the students at class 10, 11, and 12 level, or even anybody who wants to really keep this set of doodles as a concept map of de Broglie's hypothesis. So I appreciate your presence during this lecture. And on behalf of IAPT, I once again thank you. And I will be back with you immediately. Here I am. And I'm stopping sharing the screen. So I am here. And what we can do now is I will request Professor Govinda Lakhotia to once again give the same test which we gave to the students in the beginning. And let us see what improvement is there. We will try to gather some statistics now. By the way, let me tell you, dear students and the teachers, that this is how physics education research actually works, where we try to understand the learning gaps among the students. So, Govindaji, have you shared it? So thank you. It is 1:45. I will come to you at 1:55. I hope you will have wonderful time. Attempt this QR only, not on the previous link.
All of you must attend. Will be your attendance.
Professor Ahluwalia from Vidarbha University Physics Associations. And I also thank Dr. Panwane and Dr. Chimankar for associating UPTA in this activity. As through this particular enhancing knowledge through Doodles in the International Year of Quantum Mechanics. Now, Ahluwalia sir has delivered a very beautiful lecture, and that lecture is not complete if that has not ignited your minds. And ignitation of your minds will be through your questions only. And I hope many of you have generated some doubts or some questions. And now this session is open for the questions, not only for the students and teachers present in this particular hall of the postgraduate teaching department of physics, but also for all who are present online through this Zoom platform. And now this session is open for the questions. If any questions from the audience, or
So I will be very much happy if I can see some response from the students in terms of questions or otherwise also. First thing which I want to ask you is at different places who are sitting, please raise your hand if you have enjoyed the lecture. If you have enjoyed the lecture, raise your hand. If you didn't enjoy the lecture, don't raise your hand. Okay, good. One thing. Second thing is, did you see that how we brought a very interesting thing in the lecture? And that was simultaneously आपका टेस्ट भी हो रहा था. पहले भी टेस्ट लिया हमने, बाद में भी टेस्ट लिया. And this is the same trick which Amitabh Bachchan, makes use of in कौन बनेगा करोड़पति when he asks for audience poll. So ये आपका audience poll भी था आपकी अटेंडेंस भी थी और आपकी सबकी अटेंडेंस लग गई है। गोविंदा सर को हम जरूर बोलेंगे कि आपको वो ना आपका जो स्कोर है उसकी ईमेल भेजें, और हम आपके साथ स्टैटिस्टिक्स भी शेयर करेंगे किस चीज़ के, कि आपने जो एज ए टीम कितने लोगों ने पूरा स्कोर किया, कौन से क्वेश्चन आपको टफ लगे, पहले क्या हालत थी और लेक्चर के बाद आपकी हालत कैसे इम्प्रूव हुई। So, these are the modern ways of doing the things. For us in IAPT, whole of the country is a big classroom. Can you say that we can reach out to each one of you anywhere? Come on, let's make this thing happen through the portals of Indian Association of Physics Teacher. Dear students, let me tell you, if you are not aware of this, IAPT has got a student membership also. You can join us. You will receive every month a bulletin. You will also receive information about such programs which we conduct. We also are holding these days a series of monthly seminars on International Year of Quantum Science and Technology. Last time, we conducted a very interesting interview in those seminars with Professor Ghatak. I hope you have heard about Professor Ghatak's name. He has written one of the best books in the country on quantum mechanics. So you are welcome. Come near the mic. Ask me the question. Tell me your response. Yes. Raise your hand. I think even teachers can begin. You can give your remarks, sir, if you can come in front of the mic and talk about it.
Yeah. Question.
So,
There is one question in the chat box, if you can see.
yeah, I'm not able to see
Please,
in
few words on experimental setup, that is physical surrounding that determines the electron poses as particle or a wave. So they would like
once again.
listen something on experimental setup.
Okay, now look, these experimental setups are a common thing these days. In the one thing which I didn't tell you was this, that in 19, immediately after the coming up of these experiments, people started thinking of making that transmission electron microscope. In fact, in my doodle, I talked about the design part also. So what is needed for conducting this kind of an experiment? In PG and undergraduate departments, there is a set of experiments possibly which can help us to see the possibility. We require an electron gun, which you can very easily produce. The cathode ray tube is nothing but that thing. You require a gold foil if you want to do Debye-Germer's experiment. But all this thing has to be housed in a vacuum. So the vacuum technology plays a very crucial role in the success of these experiments. So these are not that we do it in open. We have to have a vacuum of the very high order. This is second thing which we would like to really keep in mind. Third thing is, when we are able to see it, that our setup is there, we want to record things. In the case of Davison-German experiment, it was nothing but a fluorescent screen on which the results were actually observed. In the same fashion, the way you observe the pictures on the television screen itself. I had one of my first televisions in my home, which was nothing. I used to say CRT in my home. People used to say, "What is this CRT? This is a television for us." I used to tell them, no, it is not a television. It is a television for you. For physics wala, it is nothing but the cathode ray tube. So see, cathode ray tube was already there on the scene. And that is why G.P. Thomson, who was J.J. Thomson's son, what he did was he chose a cathode ray tube as a chamber for seeing the diffraction of the electron waves. In that tube, the gold foil was actually hung for the electrons to fall and get transmitted. Now try to see, it is a very different experiment as compared to what you call as the Rutherford's gold foil experiment. He was focusing only on a single atom. Here we were focusing on all the crystallites which were making the gold foil itself. Now, similarly, in the case of Davison-Jabber experiment, we required that electron gun. They were thrown on a nickel crystal for a particular planes of that crystal itself, and it was like Bragg's diffraction which was happening, and you could see when is the maxima is occurring with the help of a detector. So this is what, if I have understood the question rightly, this is the answer to what you have asked me. Okay, yeah, come on.
Anyone else would like to ask? Those who are attending online can even text in the chat box.
Deshmukh ma'am, can you hear me? And was she there? She was there somewhere. Okay. Radhika Deshmukh. Yeah, she's here. She has joined from Amravati, if I am right.
Yes, sir.
So first of all, thank you very much, Physics Department, Nagpur University, for allowing me to come to you from the mountains and talk to you. Simla is very cool. I know Nagpur must be very, very hot.
Now I invite
Good morning, one and all present here. Sorry, good afternoon. Okay, good afternoon. Okay. So, as a part of the International Year of Quantum Science and Technologies, the Indian Association of Physics Teachers, IAPT, has announced a quantum physics outreach program for PG student and research student and faculties. This initiative has taken to enhance and awareness of quantum science and its related technologies through the focused discussion on various scientific and significant topics on quantum science. As a part of this program, today we pleased to organize this excellent and informative lecture of respected Professor Dr. Ahluwalia sir on de Broglie hypothesis of matter wave leading to the electron microscope. And the today's program has organized by Department of Physics, RTMNU, and in collaboration with IAPT and Vidarbha University physics teacher. And sir has enlightened all of you on the topic de Broglie's hypothesis converted into the technology. Sir has also started his lecture from the beginning of quantum era, means from the equation of E equal to h mu. Okay. And that de Broglie hypothesis is converted into the technology, and technology is the transmission electron microscope, TEM. Sir has also discussed the historical work in quantum science. Sir has also discussed the wave particle duality converted into the wave equation. That is also important. And lastly, sir has discussed very nicely quantum doodles. That is how the information of de Broglie hypothesis into the technologies of electron microscope. And one thing is very important here, test before and after the lecture. It's a very nice idea for judging the student performance and improvement before and after the lecture. And sir has discussed all the development of quantum science converted into the technology very nicely, present as de Broglie work very nicely and very simple manner. Uh, then in future, our department will cooperate to all IAPT activities. I assure you, IAPT Vidarbha region and Maharashtra region also. I think all have enjoyed this. I think all have enjoyed this insightful lecture, and sir has enlightened all young minds on quantum science and technology. So thank you very much to respected Professor Dr. Ahluwalia sir for your very nice and informative lecture. I also thanks to Professor Anwani sir, Professor Lakotia sir, Professor Kondawar sir, Professor Valikundwar sir for taking pain to organize this lecture. I also thanks to Professor Acharya Madam, Professor Abhay Deshmukh, Professor Ubade Madam, Dr. Amit Bansod, and all teachers and all students from all the colleges and institutes present here. Thank you very much. Thank you and thanks to all.
Thank you. Thank you very much, Govindaji. Thank you for all the help. And Anwane sir, thank you very much. I think we have now a very big family of IAPT in the Vidarbha region. I am grateful to the physics department here, grateful to the Vidarbha Physics Teachers Union also. They have played a very big role. Sir, whenever you want to do any activity, think of IAPT. IAPT is very much there to help you around. And what I'll do is I will write down for your purpose the website of the IAPT also, which is the official website. Dear students, you just go on this website. I'm just typing it and try to see what a wealth of information is available to you there. We are for whom? For students. That is our motto. Students are the most prime stakeholders for us as far as IAPT is concerned. If we find that you have learned something, we are the most happy people. And wish you more such programs in future also under the banner of IAPT and in close collaboration with Nagpur University, Vidarbha Teachers Union, and the other colleges who are around here in Vidarbha region. So if you now say, I will just say only one thing, and that is, I am very happy that you were there with me. Thank you very much.
Well, thank you. Thank you very much, sir. Dear students, respected faculty members, and the guest, as the coordinator of this enlightening event, I would like to extend my heartfelt gratitude to everyone for joining us today for the Quantum Physics Outreach Program. Your presence signifies a commitment to advancing our understanding of quantum science and its transformative potential in technology. Firstly, I would like to express our sincere appreciation and gratitude to our leader, our president, Professor P.K. Ahluwalia, sir, our esteemed resource person and the Central President of Indian Association of Physics Teachers. Thank you, sir, for sharing your invaluable insights on de Broglie's matter wave hypothesis and its implications on the development of electron microscope. Your way of delivering session was slicing on the cake and has undoubtedly enriched our knowledge and sparked our curiosity for sure. Special thanks to Head of the Department, Professor Chimankar sir, Convener of the event, Professor Kondawar sir, Co-Convener of the event and President of Gupta, Professor Valikundwar sir, Professor Abhay Deshmukh sir, Senior Professor Smita Acharya Madam, Dr. Seema Ubade Madam for their support and presence in this program. Thank you very much for your steadfast association, which has made today's gathering possible. Lastly, I would like to thank all faculty members and postgraduate students for your active participation, both in person and online. With a special mention, Shivaji Science College, Nagpur, Shivaji Science College, Amravati, Vidya Bharati Mahavidyalaya, Amravati, Department of Physics at Gadchiroli University, Amolak Chand Mahavidyalaya at Yavatmal, and other associated faculty members of Bukta. Your enthusiasm and engagement are what makes events like this truly impactful. We hope you found the discussions insightful and inspiring. Let us continue to explore the fascinating world of physics together and encourage one another in the academic pursuits. Thank you once again for being here today. Thank you very much, Ahluwalia sir. Looking forward for such fantastic sessions ahead. Thank you very much, sir. With this note, I would like to conclude the session.
Thank you. Yeah, please. Thank you very much and bye.